take suppose para-nitrochlorobenzene. In that, what you need to do is you need to just supply some higher temperature, which is around somewhere 443 Kelvin, and there is no high pressure condition required, and the reaction becomes simpler or easier. So therefore, when you react para-nitrochlorobenzene with the aqueous NaOH only at 443 Kelvin, the product formed is the para-nitrophenol. So you can clearly see that the substitution of the Cl actually takes place very easily when you have added any electron withdrawing group into the ring. You add two groups now, two electron withdrawing groups. So for that, suppose we have ortho-para-dinitrochlorobenzene. In this case, reaction takes place at 368 Kelvin itself, and the product formed is ortho-para-dinitrophenol. So what you can clearly observe over here is that the moment you add more number of electron withdrawing groups, the reaction becomes easier. Similarly, if you add one more electron withdrawing group, that will call it as a 2,4,6-trinitrochlorobenzene. In this case, you just need to warm it with the aqueous NaOH, and it will form, that is the picric acid, which is known as 2,4,6-trinitrophenol. So therefore, if you want to carry out the nucleophilic substitution reaction of aromatic compounds under the ordinary conditions, what you need to do is that you add some electron withdrawing group, because what actually electron withdrawing group does is that it withdraws electron from the ring, and hence it facilitates the weakening of the bond between this carbon of the benzene ring and the nucleophile attached to it. So therefore, in this case now, what you have observed is that you can carry out the nucleophilic substitution, that is by the SN2 mechanism. You can carry out in the aromatic compounds, but only if you add some electron withdrawing groups. The next example or the next reaction for the aryl halides we have is that you take chlorobenzene and you heat it, that is with the steam, at 700 Kelvin, it forms phenol. It is again following the SN2 mechanism only. Now the next reaction which we have is that you take again chlorobenzene and you react it with the CuCN, that is copper cyanide, and at 473 Kelvin in the presence of pyridine. So basically what you get is the cyanobenzene. It is again the SN2 mechanism. Now the cyanobenzene, or you say any cyano compounds, it could be RCN or it could be ARCN, that is aryl cyanides or the alkyl cyanides. These are actually very useful. How? Because when you carry out the acidic hydrolysis of the alkyl cyanides or aryl cyanides, it basically forms carboxylic acid, it is RCOOH. So for the acidic hydrolysis, what we add is the water in the presence of H+. And when you carry out the basic hydrolysis, then basically it forms the amide, that is RCONH2. For the basic hydrolysis, the reaction conditions are like, or you see the reagent we use is the hydrogen peroxide, is H2O2 in the presence of OH negative. And when you react RCN or ARCN, that is aryl cyanides, with the sodium in the presence of alcohol. In the organic chemistry, when we say alcohol, then it is by default it has a meaning, that is we are adding ethanol. So when you take sodium and ethanol, it basically reduces the C triple bond N to the 1 degree amine, and therefore it forms RCH2NH2. So therefore, you can clearly see now that how useful are these cyano compounds, because they can form carboxylic acids they can form 1 degree amine. They also can form amides. Now the reaction of the RCN or aryl cyanide with the sodium in the presence of ethanol, it is basically known as the Mendius reduction. Known as Mendius reduction. Okay, the